Welcome to Cosmos Explorer. I'm Dr. Eugene. Today's theme is capturing a star on the brink of a supernova. A research team led by Dr. Kilpatrick of Northwestern University has successfully identified a star just before it exploded, using data from the James Webb Space Telescope. This marks the first published identification of a supernova progenitor with the James Webb Space Telescope. This result is a major step toward solving the missing red supergiant problem, a mystery that has puzzled astronomers for many years. The stars shining in the night sky are much like us. They are born, they change over vast timescales, and eventually, the time comes for their lives to end. In particular, stars far more massive than our sun trigger one of the most violent events in the universe at the end of their lives, a supernova. When a star exhausts the fuel that keeps it shining, its core can no longer support its own weight and collapses rapidly, causing a violent rebound that blasts the outer layers into space. In one of the most violent explosions in the universe, a star is torn apart, scattering the elements forged deep inside it into space and helping drive the chemical evolution of galaxies. While we often think we understand stellar evolution and these explosions well, the exact state of a star in its final moments, just before the blast, has remained a mystery. Until now, the state of a star immediately before an explosion has been studied using two primary methods. The first is to examine the remnants left behind after the explosion and work backward from them. The second is to search archival images taken before the explosion and identify the progenitor star directly. First, let's look at the method of examining supernova remnants. A supernova remnant is a nebula-like structure in which the outer layers of the exploded star glow as they expand outward. In the high-temperature, high-density environment of the explosion, elements heavier than iron can be forged. At the same time, the expanding gas is rich in elements like carbon, oxygen, and silicon. By observing these remnants, we can confirm how supernovae supply heavy elements and dust to the universe. When explaining supernova remnants, they're sometimes compared to fireworks. The reason fireworks glow in various colors is the flame test, reaction of metals mixed into the gunpowder. A flame test is a phenomenon in which different elements emit unique, vivid colors when placed in a flame. For example, lithium glows red, sodium glows yellow, copper glows blue-green, barium glows lime-green, and potassium glows a pale purple. Fireworks are designed using this flame test reaction. By packing gunpowder mixed with various metals into a shell, creators can produce fireworks that shine with spherical symmetry, feature jet-like structures, or even glow in the shape of a heart. By looking at the shape and color of the glowing firework, you can imagine what metals were used and how they were arranged inside the shell. In the same way, by performing a detailed analysis of the X-rays and visible light emitted from a supernova remnant, we can determine the types and distribution of the elements within it. Then, by comparing these element distribution patterns with theoretical models, we can begin to unravel the actual phenomena that occurred deep inside the star. Notably, recent observations of young supernova remnants have begun to capture violent phenomena in which different gas layers mix just before the explosion. For example, detailed X-ray spectroscopic observations of Cassiopeia have reported evidence of shell mergers, in which gas layers mix inside the star immediately before it detonates. Another way to study the star that caused the explosion is to find images taken by chance before the event and examine the star captured there. This method brings us closer to the actual state of the star before the blast, rather than relying only on an analysis of the wreckage. However, to use this method, we must have a collection of high-resolution images taken long before the explosion occurred. Fortunately, in modern astronomy, many beautiful nearby galaxies are observed for various purposes, and these images are stored in vast data archives. Therefore, when a supernova occurs in a nearby galaxy, we can go back to past images and search for the progenitor star. In fact, Images of nearby galaxies captured by the Hubble Space Telescope have been incredibly powerful, and there have been several successful identifications of stars before they exploded. Furthermore, we are even starting to find clues about stars that may have collapsed directly into black holes without producing a visible supernova. However, as these analyses progressed, a new problem emerged. Bright red supergiants were not being found as often as expected. This diagram summarizes the evolutionary path of a star from birth to its end. On the far left, you see the place where gas and dust gather to give birth to stars. Once a protostar forms and nuclear fusion begins in its core, the star shines steadily, and its final path is determined by its mass. The upper part of the diagram shows the evolution of stars much heavier than the Sun. It has long been thought that these massive stars become red supergiants, stars that have cooled at the surface and expanded significantly just before the end of their lives. Since red supergiants are large and bright, we expected them to be easy to find if pre-explosion images were available. In reality, however, even when searching past images of supernova sites, bright red supergiants have consistently been missing. This is known as the missing red supergiant problem. Several possibilities have been proposed to explain this. One is that the red supergiant is not the final form before the explosion, and that the star changes into something else. In fact, there have been reports of cases in which a star appeared to transition from a red supergiant to a state like a yellow hypergiant. Another possibility is that the red supergiants have simply become invisible. As the end of their evolution approaches, stars shed massive amounts of material, and dust easily accumulates around them. Since dust strongly blocks visible light, a star can appear very faint even if it is right there. Therefore, to find these hidden stars, another possibility is that the red supergiants have simply become invisible. As the end of their evolution approaches, stars shed massive amounts of material, and dust easily accumulates around them. Since dust strongly... This time, the research team led by Dr. Kilpatrick succeeded in identifying the progenitor of SN 2025 PHT, a supernova discovered in the nearby galaxy NGC 1637, using images from the James Webb Space Telescope. This supernova was discovered on June 29, 2025, by an automated survey called ApJL. About 1 month after the discovery, the research team used the Keck Observatory in Hawaii to obtain a spectrum like this, revealing that this supernova is a Type 2P. In fact, the spectrum clearly shows hydrogen emission lines, which are the hallmark of Type 2 supernovae. A Type 2P supernova is a typical explosion triggered by a star far more massive than the Sun at the end of its life. This means the progenitor star was likely a red supergiant. Therefore, if images taken before the explosion exist, we should be able to identify that red supergiant. Furthermore, NGC 1637, where the supernova occurred, is located about 39 million light-years away, which is considered very nearby on a cosmic scale. This proximity allows us to resolve individual stars within the galaxy and identify the specific progenitor if images from Hubble or the James Webb Space Telescope are available. The research team checked whether the two space telescopes had captured images before the explosion. They found that both telescopes had acquired images in 2024 using various filters. This background image was actually taken by the James Webb Space Telescope, and the location where the supernova occurred is marked by the white square. When we zoom in on the region where the supernova occurred, it looks like this. This image combines data from Hubble and the James Webb Space Telescope, and a bright red source stands out, suggesting the presence of a red supergiant. When we break it down by wavelength, it looks like this. In Hubble's shorter wavelength images, no clear star is seen at the explosion site. On the other hand, in the James Webb Space Telescope images, a bright source is clearly visible. This means that while it emits little detectable light at shorter wavelengths, it shines brightly in the infrared. This shows that the star was really there, but dust absorbed much of its shorter wavelength light, making it far harder to see. To investigate these characteristics, the research team created a spectrum like this. The horizontal axis represents wavelength, and the vertical axis represents brightness. The pink circles show the upper limits on brightness obtained by the Hubble Space Telescope. The red circles show the actual brightness of the source identified by the James Webb Space Telescope. To explain this data, the research team drew 3 model curves. The orange line is a model combining a red supergiant with carbon-rich dust at a temperature of about 790 Kelvin or about 520 degrees Celsius. The green line is a model combining a red supergiant with silicate-based dust. The blue line is a model of pure black-body radiation at a temperature of about 1470 Kelvin or about 1200 degrees Celsius. In this case, we assume that only the dust itself is glowing. Comparing them like this, it's clear that the pure black-body model, shown by the blue line, cannot reproduce the data from the near-infrared to the mid-infrared. However, if we assume that dust exists around the star, the consistency with the data improves dramatically. Furthermore, the accuracy depends on the type of dust. The brightness around 7 to 8 micrometers is particularly important. The silicate model tends to show a prominent peak in that region, making it a poor fit to the observed points. In contrast, the carbon-rich dust model overlaps much more smoothly with the observational data. This suggests that the dust surrounding the star before the explosion was likely carbon-rich rather than primarily silicate. In addition, the team found that the progenitor itself was consistent with a red supergiant, which is exactly what we would expect near the end of a massive star's life. This result is a major step toward solving the long-standing mystery of the missing red supergiants. Red supergiants really do exist just before supernova. However, they are shrouded in dust, and their visible light is heavily blocked. In this specific case, the dust made the original red supergiant appear more than 100 times dimmer than its true brightness. Therefore, with the James Webb Space Telescope's infrared sensitivity and resolution, we may be able to uncover many more dust-hidden stars just before they explode. We look forward to future discoveries. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.